Hello everybody, my name is Kenji Shibata. I'm from Utsunomiya University, Japan. Today I'm gonna talk about mobile robot motion planning based on time-delay CNN with open space image input for march obstacle avoidance. In recent years, mobile robots have been assisting with human works, for example, transportation, cleaning, guidance, and so on. The robot need to move autonomously in warehouse, train station, and airports. These environments contain multiple obstacles such as shelves, desks, and people. In such environment, robot must move safely and efficiently, so robot need to avoid the obstacle. Therefore, the purpose of this work is march obstacle avoidance by mobile robot. In our previous work, we proposed a motion planning focusing on open space. Open space is an area which is not occupied by obstacles. This figure shows the motion planner proposed in our previous work. The motion planning is to determine the following outputs for sensor inputs: linear velocity and angular velocity. The input to the motion planner are open space images and open space difference images. Open space image is generated through unit and YOLO. And then the open space difference image is generated from the temporal difference between two open space images. With this approach, the robot successfully avoided multiple obstacles. However, immediately after avoiding an obstacle, the robot sometimes plans the motion to reorient itself toward the destination. This figure shows the angular velocity outputs during both instruction and autonomous navigation. It can be seen that the robot was instructed to move straight for a few seconds after avoiding an obstacle, and then to adjust its orientation toward the destination. That is reorientation. On the other hand, during the autonomous navigation, robot planned the motion to reorient itself immediately after avoiding an obstacle. As a result, robot may fail to avoid the obstacle and be at risk of a collision. To discuss this result, we focus on the RGB open space and open space difference images taken just before the straight and reorientation motion. And we can see that the two RGB images are highly similar. Therefore, the generated open space and open space difference images are also similar. Although the instructed motions were different, the input image in the upper and lower figure are highly similar. Therefore, the planning different motions based on similar image input is difficult. To address this challenge, we focus not only on the current image but also on the past images. Although the two current images are highly similar, the corresponding image taken 2 seconds earlier are clearly different. Therefore, the past time series image are also used as input in addition to the current image. This enabled the motion planner to associate the input image with the different motion outputs instructed for each case. For these image inputs, we propose a motion planner based on time-delay CNN. This figure shows the architecture of the motion planner. 3 open space images captured at different times are concatenated along the channel dimensions and used as input. And then the last layer, the linear velocity and angular velocity, are resulted as the outputs from the motion planner. Here, let us explain the setting for imitation learning. This figure shows the occupancy grid map built by robot beforehand. Robot moves from S towards Z while avoiding the obstacle. In the immersion instruction, robot avoided the obstacle. The robot avoided to the right for obstacle A, and the robot avoided to the left for obstacle B. Next, let us explain the setting for navigation experiment. In the experiment, the previous motion planner priors DOS and the proposed motion planner priors TD are applied to the robot. In each of the obstacle A and B, robot repeated the navigation trial 5 times in total. This is the navigation result. For obstacle A and B, robots successfully avoided obstacles in all the trials regardless of the motion planners. These two movies are result in the navigation experiment for obstacle A. The movie on the left is the robot based on the previous motion planner, and the movie on the right is the robot based on the proposed motion planner. The robot avoided to the right for obstacle A and to the left for obstacle B. And then the relative distance at which the robot planned avoidance motion was approximately 5 meters, which is almost the same as that during instruction. Next, we focus on the straight motion's time after avoiding the obstacle. This figure shows the angular velocity output based on previous motion planner. The robot based on the previous motion planner did not plan the straight motions after avoiding the obstacle. On the other hand, as shown in this figure, the robot based on the proposed motion planner planned the straight motions for 1 second after avoiding an obstacle. This is the same time as the instruction, and this result more closely matched the instructed motions than the result from the previous motion planner. Next, we further conducted the navigation experiment with multiple obstacles. The experiments are conducted in both simulation and real-world environments. This figure shows the environment in which the four pedestrians walk straight toward the robot. The same motion planner priors TD is applied to the robot. It should be noted that this environment was not used during the motion instruction and is therefore unknown to the robot. The robot repeated the navigation trial 5 times in total. And then this figure shows the robot used in the experiment. The robot is equipped with a single camera and 2D LiDAR. The camera is used for object detection and segmentation. And then the 2D LiDAR is used for localization. This is the navigation result in simulation environment. The robot based on the proposed motion planner successfully reached the destination while avoiding the obstacles in all the trials. This movie shows a navigation result in simulation environment. We can see that the robot avoided multiple obstacles and reached the destinations. And then this figure shows a navigation trajectory of the robot. In some cases, robot avoid the obstacle or fall on the left side by moving to the right and to the left. This is because the differences in open space image inputs cause the different motion outputs. And then this is the navigation result in real-world environment. As shown in this movie, the robot avoided these obstacles and reached the destination in 4 out of 5 trials. For each obstacle, robot avoided the obstacle from a distance similar to that in the simulation. In one trial, however, robot failed to avoid the obstacle or fall on the left side and was forced to make an emergency stop. To discuss this failure of obstacle avoidance, let us show you the feature map and the RGB image taken just before the failed obstacle avoidance. In the map, as shown in this figure, the feature was extracted on the right side. Therefore, the robot planned the avoidance motion to the left. This motion was correct as instructed. However, as shown in the RGB image, the pedestrian was walking straight toward the robot from the front right. Therefore, the robot avoided to the left and moved to cross to the pedestrian and eventually forced to make an emergency stop. This is because the robot was instructed to avoid the obstacle approaching directly from the front, and no instructions were provided approaching from diagonal directions. With the additional instructions, however, the robot was able to avoid the obstacles moving in different directions. This is the conclusion of this presentation. The purpose of this work was merge obstacle avoidance by mobile robot. However, a reorientation motion was planned immediately after avoiding an obstacle. For this challenge, we proposed a novel motion planner based on time delay CNN, which uses past time series image as input. As a result, the robot was able to imitate the instructed motions, and finally, the robot based on the proposed motion planner successfully avoided multiple obstacles in both simulation and real-world environment. That's it. Thank you very much for the kind attention.